Ladies and gentlemen, your attention please. Welcome to Science Expeditions at the UW-Madison Chemistry Department. Please do not use any flash photography during the presentation. Thank you for your cooperation. And now, without further ado, UW-Madison lecture demonstrator, Jim Maynard. I wear a lot of hats. This is one of my hats, one of my duties. It's one of my favorite duties. What I do is set up experiments for other people to do and enjoy. And if you pay attention, we're going to see a lot of really interesting things. There'll be sound and bubbles, color changes, even explosions. But remember, this is all about safety too. Nobody has any fun if they're not safe. So you notice I have a fire extinguisher, and it works. There's another there, and then there's one more in the other room. And the truth is that we don't expect anything to go wrong, but if it ever did, we are ready for it. So let's begin. So for my first set of experiments, I am going to focus your attention on the large spherical objects hovering in the air. Okay. Now, when you watch science experiments, a lot of times what you want to do is practice your skills of observation. We're going to talk a little bit about this as we go. But the important part is paying attention is how you get the most information when you do experiments. So I'm going to start over here with this green balloon right here. And how we're going to test this lighter than air gas is to see how reactive it is. And so how we do that, in this case, I'm going to use this. I call this my actuator of science. So we're going to get started with it. So I'm adjusting it. And you know, there's a lot of chemistry going on right here. So a guy named Michael Faraday wrote a 186-page book about candle flame. So there's science in everything. Science is part of nature. It's part of the world we live in. We live in a chemical world. So let's begin. On the count of three. 1, 2, 3. All right. So what kind of gas might that be? Just call it right out. That's right, it's the gas helium. Helium floats, it's lighter than air, but it's not reactive very much. It's already very stable. So in science, we repeat the experiment. So let's do that. On the count of three. 1, 2, 3. Was that the same result as the first time? Exactly the same? It's pretty close, wasn't it? Okay, so that's the green balloons. I'm going to now move on to the second set of balloons, and these balloons are yellow. Okay? So this is a different gas, and we're going to test it the same way we tested the first one. Ready? On the count of three. 1, 2, 3. Ooh! So was that the same gas? No, that was the gas hydrogen. And that's a combustion reaction, and combustion happens when the hydrogen gas in this balloon reacts with the oxygen in the air to form water and release energy. So, in science, we repeat the experiment. So I'm going to repeat this experiment, but in this case, I'm going to repeat it in the dark. And why? Because when some of the information we want is visual, we want to reduce the amount of background noise that we have, which means in this case, noise is light. Anything that prevents you from knowing what you want to know or getting the most information out of your experiment is what I'm talking about. All right, with the lights down. Now, with the lights down. Yay! All right, so here we go. Hydrogen balloon in the dark. On the count of three. 1, 2, 3. All right. Now, with the lights back up again. Now, when you saw it in the dark, did you get a better view of what really happened, or was it better in the light? So that's very important in science, that we set up the conditions so that we get the best results from our experiment. So now I would like to add the fact that the first two balloons were green, right? And they didn't make a lot of noise. And then the yellow two balloons were yellow, which is not green, and they were a little louder. So these are red balloons. And if you think of your stoplight, we have green, we have yellow, and we have red. These are a little louder still. And in fact, these are loud enough where I want you all, when the first reaction happens, to take your fingers, put them in your ears, and cover them. And then put your hands over. And you're doing this to protect your hearing. This can be pretty loud, but it's really cool. Now, I can't plug my own ears and do the experiment, so I have this. So let me know. Yeah, do y'all look ready? Okay, I see some of you don't have your ears plugged. Okay. On the count of 3. 1, 2, 3. So that reaction is the same reaction as the other one, except for this balloon has a mixture of 2 gases, hydrogen and oxygen. So it's louder and it's faster and it's an explosion because it doesn't have to mix with the oxygen in the air to do its chemistry. It does its chemistry right there with the oxygen that's already in it. So now what I'm going to do is repeat the experiment, because that's what we do in science. And I'm going to do so with the lights down, but I'm going to give everybody a second to find a place where they're not moving in the dark. All right, I think that's close enough. With the lights down. All right. I thought I was going to have to go back there again. All right. Second repeated experiment. This time, hydrogen, oxygen. On the count of 3. 1, 2, 3. All right. All right. So, now we have run a series of experiments with these 3 gases, and we've learned a lot about how things are reactive. And now I would like to draw your attention to my next experiment. All right, so donning safety gear. Do you see in front of me I have, how many cylinders do I have here? What do you think is in them? How would you describe them to someone who is not here? So I see, so if I'm talking to my friend in Britain who wants to see this and he can't be here and all I have is a radio, I would tell him I have 6 ungraduated cylinders, approximately 1 liter in volume. They're approximately a half a meter tall, and they're filled with 6 liquids, 2 clear and purple liquids, 2 clear and pink liquids, 2 clear and blue liquids. So this is setting up observations so that you have a way to convey information to other people. Now let me ask you a question. Is it easier to see them like that or like this? So we are fixing our experiment so that we get the maximum amount of information out of the science we do. And in here I have some dry ice. Dry ice is solid carbon dioxide. It looks like this. Carbon dioxide sublimes or goes directly from a solid to a gas without forming a liquid in these conditions. We call that sublimation. Can you say sublimation? That's really good sublimation. I love that. All right. So now what I'm going to do is I'm going to take some of this dry ice, I'm going to put it in some of these cylinders. Now, I have these things set up together for a reason. One of them is the experiment, and the other one's called the reference. So when you do science, you want to have a value to compare the change of something with its original state. So they all start, in each experiment, start the same. And now I'm going to add the dry ice to these things in a certain order. And you'll see what I mean. So that's another proof we have sublimation, right? Because now you can see the bubbles that were being produced over here as gas. So let's do another one. So I think we have some chemistry going on, right? Marvelous. And then this one. So these things have all changed some. Look at this one on the middle. Look in the middle. That's the nice one. All kinds of stuff's going on in that one, right? These are called indicators. And in a long time ago, indicators were used very frequently in science to detect a change in chemistry in other experiments they were running. And so nowadays, a lot of this is done with scientific instruments, and it's not quite the same uses, but it's all very inspiring. And just think how clever it is to be able to figure out how to determine how far your experiment has gone when it's 150 years ago and there aren't a lot of technology available to do these things. And so I think it's very interesting. All right, so now I'm going to drop a piece of dry ice in this purple one just because I like it. How many color changes? 1, 2, 3, 4, 5. All right. So this is a great experiment. And stuff like this is basically working with acids and bases. And I have a colleague named Professor Bassam Shakashiri. He has a wonderful website called scifun.org. And you can learn all about stuff like this on his website, scifun.org. You don't have to write it down. You just say it a couple times. You'll memorize it. And I was a student in Bassam Shakashiri's class a long time ago. So, all right, let's do another experiment. We don't have all day, right? All right, so now for this experiment, I have some hot boiling water, and I'm going to need my gloves still, and then I have a pan. So this thing's empty right now except for what? Air, that's right, very good. And let's see, I got my hot boiling water over here, but you know, I cannot seem to find, I had a bucket of dry ice out here somewhere. Hey, can somebody bring me out a bucket of dry ice, please? Oh, there you are. Come over here. Come over this way. There you go. I'll just take that from you for the moment. All right. All right. All right, Bucky, let's do an experiment together. How you doing? Good? Wonderful to see you here. Thank you so much for coming to my lab. You can never know who's going to show up in this laboratory, and that's what makes it so great in some ways. Come on out here. We're going to do an experiment right now. So take your bucket of dry ice. Hold on to this. What I'm going to do is I'm going to put some hot boiling water in here, right? Okay, and then I'm going to have you pour in that dry ice. So here's my hot boiling water. We pour this in ever so slowly. Okay. And there it goes. Yeah, don't touch too hot for you. All righty, and we're pretty much ready. I want you to dump all that into that bucket right now. The whole bucket, right in there. Go. All the way, hard, fast. There you go. Way to go. Yeah, we're still here. Wow. You're good at this. So this is all condensed water vapor, and this is how they used to make fog in the movies. So they would heat up some water, they would put some dry ice, they would get a fan, and they would blow it wherever they wanted to. And so nowadays, I'm sure there's other ways to do it, but they can't be this much fun. They just can't be. So there you go, Bucky. Thanks. So how you doing this year? So I know Bucky's a really good student, and he probably just got through midterms. And he's been doing so well that I actually gave him a bonus experiment. So we're going to do another one. All right, let me move this guy because he's really bubbly. All right. All right, Buck, here's what we're going to do. So I don't need those either, but here, I'll just, you know what? All right, good. So this is our next experiment. So in here, we have a 5-liter round-bottom flask with a clear and colorless gas inside. Okay? And then we have a couple of pieces of tubing. One goes down into this liquid, this clear and colorless liquid. And then we have this is called a stopcock. And then I have this little tube. So what I'm going to do is I'm going to take this off and put this little squeeze bulb right on here. And once I get it on there, then Bucky's going to do part of the experiment for me. So I'm going to open this stopcock. All right, Bucky, if you could please squeeze the bulb. Give it a good hard squeeze. Ready? Ah, yes. Squeeze again. Good and hard. All right, there you go. You can stop now. Yay, look at him go. Amazing. All right, so what could be going on? Lots of very interesting things are going on here, right? Sure is. That's a nice color. I like it a lot. What do you think? Yeah, not bad, right? Hmm. So what's happening here is there's a gas in here that's very soluble in water. And Bucky put a little bit of water in there. All the gas inside there went immediately into that little bit of liquid. And then that drew a vacuum, which means the pressure went down in here, but the pressure outside us doesn't change. So then the pressure of the air forces it down. It goes up through the tube, and you get this lovely fountain effect. And so this is called the ammonia fountain. I will admit to you, I like this one particularly. It was one Bassam did for me. And when it happened, I was like, what? Because I had no idea. But now I know a lot about it. And that's what you do in science is you like something, you learn about something. And so that's what makes science cool. Because you don't just watch. This isn't a magic show. We'll tell you the tricks. All right. So you have time to hang around for a while there? Oh, it's cool. Nice and cool. You have time to hang around for a bit? Okay, great. Oh, one other thing I wanted to ask you. So when you graduate, how many years do you think it's going to take you to graduate? What are we trying? What's our goal? How many is that? We're not there yet. 3, 4? Oh, 4. Okay. 4 years. So Buggy's going to graduate in 4 years, I'm pretty sure. And, well, okay, iffy. But that's our goal as college students, to get in and reduce your costs and do a good job so that you can get in and out of 4 years and then go do the things in life that you really like. Okay, so I got a chair over here for you. You can just sit down. Always a pleasure, my friend. All right, so I have more experiments. I'd like to draw your attention over here for a minute. We've been doing some things with carbon dioxide, and I have another experiment that has to do with that. And I'm going to use this ladder. Okay? So, first part of this is the hardest part. We have to light all the candles. Yeah, this is the part you have to practice. Really, it is. Especially this one. Yeah, that one's really tough. Okay. Okay. You need a really good lighter for this, too. All right, so I've lit all my candles. All right, so these candles in a ladder, and now what I have over here is this container full of, well, something, right? I'll tell you right now, there's a gas in here, a heavier than oxygen gas, and I am going to now pour this gas down this incline, and let's see if any chemistry gets done. Are we ready? All right. Pouring. It's not easy. Let's see if there's anything in there. Let's see if anything's in there. Not quite as much as you'd want. So, the reason that this gas put out these candles, that it did put out, is because carbon dioxide. So the carbon dioxide in here is clear and colorless, but it's also heavier than air. And so when you pour it down the incline, if there's enough, you can see it'll put the candles out. Of course, that's why they use carbon dioxide for this sort of thing, right? It's a fire extinguisher for a reason. It works very well for that. Does not support combustion. All right, so I have another experiment I'd like to show you. All right. All right, so for this experiment, I need a candle. And like I said, an aforementioned scientist wrote a really, really long book about candles. Let's see if I can get this one to go. There we are. All right. So in my wallet, I'm going to take out my wallet for a second here. And see what I have in here. It's some things. What kind of things do you have in your wallets? Money, credit card, ID. Receipts, that's right. Penny pinching. Good. All right, so I have a bill here. I'm going to take a look at it. Here we go. And then I wanted to show you one of the properties of this. Talk about inflation. So, yeah, you got to be careful. Okay, that was a false one. This is made of flash paper. It's a very clever thing. Very much like it. But now for the second part of this experiment, I have a real one. Okay. So in this case, what I'm going to do is I'm going to dunk this real $20 bill in this clear and colorless liquid, and we're going to get it wet, and then I'm going to run an experiment on it. All right. Good and wet. All righty. Let's see what happens this time. Ooh. Okay. Yeah. So what happened, do you think? Well, let me tell you what happened. The $20 bill was dunked in this solution. This solution it's part isopropanol and part water. And so the isopropanol part is enough to be ignitable, but the water keeps it cool enough where the bill doesn't actually get consumed. This is another fun experiment, sort of testing people's sort of perceptions about how things go. All right. I have so much more stuff here to show you. This is my next experiment. All right. So this is called a bell jar. And the bell jar is used when I want to control the pressure of something. So I have a bell jar here. And I also have another little toy I'd like to show you. This is a little pump that removes air from stuff called a vacuum pump. So I'm going to hook up my vacuum pump. And I'm going to run an experiment for you. So in this experiment, I'm going to use shaving cream. Okay? Some of you may not be old enough for this yet. Unfortunately, I'm way old enough for this. All right, so I'm going to take a little of this shaving cream, and I'm going to spray it on here like that. Okay? And I'm going to take my bell jar, and I'm going to seat the bell jar oh so carefully on here. So now, right now, the pressure inside here and the pressure outside here are the same. But I'm going to reduce the pressure inside here. Let's see what happens. So, is anything happening yet? Maybe not. Thank goodness it's an experiment, huh? Another thing about science is sometimes you have to wait a little while to see the results you're looking for. So let's wait a little while and see if anything gets different. Something seems to be happening now. That's right. It sure is. That's great. This was what I was hoping was going to happen. So the pressure inside here is going down, right? It's lower and lower. But so what's happening? Why do you think this happens? Okay, so I'm going to tell you a little bit about it while it's going. So shaving cream is an emulsion, right? Which is a mixture of two phases of things. So this is an emulsion of liquid and gas, okay? Cake is an emulsion of solid and gas. Emulsions are mixtures that are not of the same phase. So what's happening is we lower the pressure, the gas inside this mixture is expanding, and the liquid goes with it. And so it retains its shape because the loss of pressure is relatively equal on all sides. And as you can see, after a while, this becomes quite a pronounced effect. So it started out pretty small. All right. So now we've gotten to the point where it's starting to touch the outsides of the glass. So have you ever wondered what might happen if you were to put the pressure back in here? That's what I love to hear. Okay, well, you know what? This is an experiment. Let's find out what happens. So I'm going to shut this valve and take this off. And as you see, the pressure is still maintained in here. But I'm going to open this valve and we're going to see what happens to the shaving cream inside. Are we ready? Deflating. Okay, so as the pressure goes up, now the structure that was being held up by the expanded gas inside goes away. And all you're left with now is the liquid part of the emulsion. Wonderful, wonderful experiment. I've always been a big fan of that one. All right. So I think I want to do, I'd like to direct your attention over here now. Okay? So not just over here too, over here and over here. So first I want to do an experiment in two parts. So this is one part. Okay. So I'll need this over here. And I'll need this. This is the other part of the experiment over here. So what I'm going to do right now is I'm going to take this hot water out of this container, this Erlenmeyer flask, by the way, and I'm going to pour it in this round bottom flask. I guess I could do it in front of you. It's not going to be that pretty. Pardon my spilling. All right, here we go. So I'm putting this hot water right in here. And I am putting this hot water in here only to heat this up. So we're going to heat up this round bottom flask. Pouring is something you do a lot of in chemistry. It's a lot of pouring. So in we go. Don't want to spill. This is hot water, really hot water. I usually wear hot gloves for this. These are my at-home leather hot guy work gloves that you would weld in, because water has a really high heat capacity. It holds a lot of heat. It stays hot for a long time. All right. Almost done with this part. All right. I always like to call it phase one. So phase one is done. On to phase two. Phase two is always better because that means phase one is done. All right. So now, let's come over here. I want to direct your attention to this part of the experiment. So in here I have some clear and colorless liquids, and I will tell you right now that one of them is a dissolved form of silver. And some of the other ones are basic, meaning like drain cleaner or lye soap. So we're going to make a complex, and I'm going to start with this. This is silver nitrate. And I'm going to stir it, and I'm going to add to it ammonium hydroxide, which is ammonia. Like household ammonia, just a little bit more powerful is what I would call it. So here's another thing you do a lot of in chemistry, stirring. All right, you can see a chemical change is already taking place, but there's more chemical changes coming. So right now, this has formed an oxide, a silver oxide, which is that brown solid. But if you add enough ammonia, and boy will I ever, look, it disappears. So now this is called a complex, and now there's a complex in solution. But I'm not satisfied enough with that yet either. So now I'm going to add some potassium hydroxide. Oh yeah. Now that's a lot of base. So now I'm going to add some more ammonia, and I'm going to recomplex this silver mixture. Okay. So stirring again, big part of chemistry, a lot of stirring. Pouring, stirring, writing stuff, talking to people. Remember, you have to communicate your science to other people because they have to be able to. It's not real science if someone else can't do it. All right, so now I have my reactant. This is a silveramine complex. And this is dextrose, or sugar, blood sugar. Okay, so now I need my gloves on. I'm going to go get my flask. All right, and here's my flask. Good, it wasn't too long a trip. Yeah, he's just poured all the water out of there that he poured in the first place. What's that? And the answer is, you'll know in a second. All right, and I got my nice hot flask. I'm coming over here to the front because I love this part. I'm going to put the silveramine complex in the flask. I'm going to put the sugar in the flask, and then I'm going to mix it in a very special way. See how it's changing color already? It's brown. It looks a little different, don't it? Let's keep turning for a while and see what happens. Oh, I'm beginning to see something. It looks like me. I can see me now. All right. You have to turn it this way. If you don't do the hip thing, it doesn't work. All right. Are you seeing a difference now in the surface? All right. So this is called the Tollens test for aldehydes. It was made in the 19th century. And what it would do is it would reducing sugars, or sugars that had a specific chemical structure, would react with the silver in this basic solution to form silver zero, thereby telling people that this particular species of sugar was in there. So this is also the way I used to make Christmas ornaments. You can see how that might work out. Yeah, now I'm tired. I've been shaking this thing for a while. You have to rest. All right. So much fun. Where's Tracy? All right. I have a special treat for you. I would like to welcome our next guest, UW-Madison Master Glass Blower, Tracy Dreyer. All right, here you go. Take this out. Okay. Yep, turn it on.
Hello. Hello. So, this is called the Wisconsin Fire Wagon. I use this for doing outreach, just like this. I'd like to show you what's going on inside here before we get going. We have propane and we have oxygen. And that's what drives this torch.
Here. Thank you.
We also have a fire extinguisher. Very important when we're dealing with fire. And, yeah.
Need a striker? No. I got a striker somewhere. Okay, good. All right.
Fabulous. So, we have a little bit of glassware right here, a nice big coil. And what I wanted to do is, instead of building a great big one like this, I just wanted to give you guys an idea of how we might go about making something like this. It's tricky. But we start with, this is called a mandrel. This is just steel. It could be copper.
They get bigger.
Yeah. So that's what we use to build this one. But this is a smaller one. And so what we're going to do is, my raw material looks like this. Hey, Bucky, nice to see you. Anyway, we heat this up. Metal, we know, expands. And then this glass doesn't quite expand as much. And what we're going to do is adjust our fire so that it softens and it wraps around. It's hot enough to move, but not so hot that it sticks to the metal. It's a little tricky. So this is just a propane fire, and if we introduce our oxygen, we can see the color change. That's also telling me that this is a much hotter flame. So what I'm doing is adjusting my fire so that it's nice and fluffy.
Isn't it amazing he doesn't have any gloves on, but he doesn't get burned? What a skill.
So glass is a very good insulator. But now I'm going to warm up this mandrel. And when we slide our glass in, there's a hole in this. We're going to just poke it in that hole. And this will just, we have a nice fluffy fire so that it's starting to warm the glass as it gets up to the point where it starts to wrap around. You can see my hand on the back here. I can sear the glass by turning it one way or the other to try and keep those foils nice and uniform. So now this will cool off, and like I said, the metal is going to shrink more, and this is going to just slide right off. And yeah, exactly. And it's going to look just like this. And so you can see that's exactly how we go about making a larger one. Just more heat and actually more people.
More people.
Yeah.
All right. Well, you have time to do a quick experiment with me?
I do.
All right. Here I'm going to have you put on one glove. Just like Michael Jackson. All right. So this is our experiment. Let me bring this over so we can talk about it. Okay. So we have two fluids here, one clear and colorless liquid, one clear and blue liquid. And we have a spiral that Tracy made. This is his own creation, which is, I find it to be very interesting that he has so many talents. Yeah. So give him a hand, won't you?
Thank you.
All right. So this is an experiment where I expect light to be produced. We're going to turn the lights off. And with the lights down. All right. On the count of three, we're going to pour.
All right.
1, 2, 3. Good point. Nice. Keep going. There you go. There we go.
Yeah.
Nice. Isn't that wonderful? So,
thank you, Jim.
This is called the luminol reaction, and it's light without heat, right? And where do you remember other things that have light without heat? Well, this is one of them. This is just a glow stick you can buy at the store. You can shake it, and light without heat, chemiluminescence. That's what this is called, chemiluminescence. So this is an energy transfer without heat. Wonderful experiment, and Tracy's a wonderful guy. All right, so for my next experiment, I'd like to direct your attention to the center of the room where I have this very large beaker. This is a 4-liter beaker. So now you've seen what a 4-liter beaker looks like. You know what 4 liters looks like. You can never unlearn this. You might forget it. Okay, so I'm going to move this over here a little bit so I can run my experiment. So this is a special stir, and then it has a light. So I'm going to get this stirring, and I have 3 bottles of clear and colorless liquids. I'm going to add them one at a time, and we'll see how the experiment goes. All right, so there's one. Now I'm just going to keep adjusting the stir rate until I get the one I want. I'm going to add a second liquid. Now I'm a lefty, so I pour from this side, just so you know. All right. So not much happening yet, but we haven't got them all in there. And so let's see what happens next. So now I'm going to adjust this vortex so that we get a good mix. There we go. I hope this is the only vortex or tornado or anything like one that you see. All right, so now I'm going to add this third experimental reagent, and let's see what we get for results. Oh, look, the color change. That's so wonderful. So as this mixes, it does this reduction. Isn't that amazing? So I've always liked the way this ends because you have this starch iodine complex, and then you get this deep, beautiful blue color. What? 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 Well, it's blue. I don't know. What's wrong? So anyway, like I said, it took high-powered scientists a long time to figure this out. What do you want me to do? Oh, well, it's blue. I don't know. So maybe you'll stand over here for a second just to see if there's a chance that I can do it. What do you want me to do? You want me to look at it? Am I supposed to look at it now? So am I supposed to look? What am I doing here? Let's see it. Can this side of the room tell me what that? Should I look now? Now? I don't want to trip on anything. Okay. All right. So, okay, let's see. Okay, all right. So, what's the difference? You guys looked at the right time because you looked all the time, where I was distracted by the many shiny things in the world. So, this is called the Briggs-Rauscher oscillating reaction. It's really special in some ways because Briggs-Rauscher were the last names of two high school teachers in Northern California. This was invented in 1973. These oscillating reactions are called Belarusov-Zhabotinsky reactions. This is the most famous one. And these beautiful blue colors are caused by the change in the oxidation state of iodine in solution. And there has a lot of different things in here. There's acid in here, there's potassium iodate, there's hydrogen peroxide, there's potato starch, manganese sulfate. It took high-powered scientists from the national academies over 10 years to understand what's going on in this beaker. What? What happens when it's not turning? Okay, so what you'll get is the same chemical change, but it won't be as uniform. The mixing is what makes it change all at once, but if you stop mixing it, what'll happen is you'll see a more layered change. This will keep oscillating until it runs out of electrons, which are supplied by the hydrogen peroxide. So as hydrogen peroxide supplies electrons, it turns into water and oxygen, and you can actually begin to see the accumulation of oxygen bubbles in here. And as you can see, now it's a little less sudden because now the mixing has to move through the solution in order to happen. So as it gets done, it'll have more and more bubbles. They're all oxygen. Okay, marvelous. All right. I'd like to direct your attention over here for a minute to this really big crank I have. And there's a clear and brown liquid in there, and then this is water. So this is the description of a different kind of fluid. So when you have water and you stir water really quickly, what happens? We just saw it, right? When you stir water really quickly, you get a vortex, and that vortex points down towards the origin of spinning. Okay? So keep that in mind. And now I'm going to turn this crank, and we're going to see what happens to this fluid. Are you ready? You have to spin really fast. So this is a non-Newtonian fluid. This is a Newtonian fluid. It acts according to the laws of macrophysics in that particular idiom. This does things that other liquids don't do. It's because these are very long polymers, and they develop an interconnectedness that makes them stick together way more than water does. It's called polyacrylamide. All right. I have a couple of more pretty good experiments to go. So let's do the next one now. So for this next one, I need a little bit of special equipment. This is my experiment. This is a powder. It's a mixture of iron and aluminum with some oxygen. It's in this flower pot. It's actually in 2 flower pots. Ceramics, high temperature. Then I have tongs, and I have this sparkler. And then, of course, who could forget this? Okay. All right, so let's get our experiment going. I've done enough talking now. So I'm going to put this in here. I have turned on the ventilation. And I'm going to hold this up because this one has a latch issue. But it's going to go in here. And then I'm going to light this. Hold this up. So I'm going to light this, and I'm going to stick it in here. And I'm going to turn the lights off when I do that. So bear with me a moment. It's worth it. All right, here we go. I have this big sparkler and some hot gloves. Light sparkler, I'm going to put it in here. We're going to shut this. I want to see some chemistry. Ready? All right. It's, as they say, it's short, but it's sweet. So this is the thermite reaction. It's a form of the Goldschmidt reaction, is a particular name. And there are a series of reactions where metals exchange oxygen and give up lots of energy. This is one of them, one of the most common ones. It's one of the least reactive ones also. So one interesting thing about this is that this is how they used to weld railroad ties together back in the olden days when they were building the Continental Railroad in the United States. So they would, if you notice, in those days what they would do is they would forge each rail tie with a half of a cup. They would join the two together to form a little containment area. They would then put some of this thermite mixture in, touch it off with a hot iron, and then it would melt like this, melting the ties together. This is what they did before electric welders. So a lot of the United States rail in the early days was made this way. This isn't just red hot, it's white hot. And this is what it looks like when it comes out. It's still liquid in there. Marvelous. You can poke at it if you like. I enjoy this part. There, see, I poked at you. Good. Marvelous. All righty. I have another experiment. All right, let's go, people. All right. At this time, I'm going to set up my final experiment for the day. And I'd like to introduce to you my two helpers for today who work in my lab. Wonderful people. Andrew Young and Kayla Bean. All right. Everybody grab a tray. So this has been a lot of fun. I hope you guys have enjoyed it as much as I have. And we're getting ready to finish up. So in this one, we have a clear and colored liquid in each one with some bubbles that is probably soap. We have a small beaker of each type. Each one of us has a little beaker like this. And we're going to add, hopefully all at the same time, we're going to add the contents of the small beaker to the large ungraduated cylinder. At the, come close, here we go. We're gonna move this a little bit. Sorry. We're gonna move this. All right, there we go. All right, are we ready? On the count of 3, 1, 2, 3. All right, so that concludes today's lecture. Thank you so much for attending. You're a wonderful audience. Don't forget, join the science expedition.